The space environment presents unique perceptual challenges unlike anything experienced on Earth. Even the most highly trained astronauts must contend with physical and psychological factors that can alter what they see and how they interpret their observations. These challenges create a complex observational environment where distinguishing between genuine anomalies and perceptual artifacts requires careful analysis. The physical conditions of space create numerous opportunities for visual misinterpretation. In the vacuum of space, light behaves differently than in Earth's atmosphere. Without atmospheric diffusion, shadows appear darker and more defined, while illuminated surfaces appear exceptionally bright. This extreme contrast creates optical illusions where ordinary objects look unusual or distorted. The absence of atmospheric perspective makes distance perception particularly challenging, like viewing the world through a warped mirror, where familiar objects become unrecognizable. Radiation exposure adds another layer of complexity. In orbit and beyond, astronauts encounter various forms of radiation that interact directly with their visual systems. Cosmic rays passing through spacecraft walls and astronauts' bodies interact with the retina or visual cortex, producing distinctive visual phenomena. These interactions create what astronauts call light flashes, or shooting stars in their vision, brief streaks, dots, or blobs of light occurring randomly in the visual field, even with closed eyes. Apollo astronauts reported seeing these flashes approximately every 3 minutes when trying to sleep. These internal visual events can be misinterpreted as external phenomena, especially during brief observations or high-stress situations, precisely the conditions under which many of our documented sightings occurred. The physiological impacts of microgravity significantly affect human vision. Bodily fluids redistribute toward the head and upper body, altering intraocular pressure and changing the eyeball shape. NASA has documented spaceflight-associated neuroocular syndrome, SANS, where astronauts experience changes to their optic nerves and retinas during extended missions, resulting in altered visual perception. These physical changes could explain certain aspects of Gordon Cooper's observations, where perception of size and distance might have been compromised. Our brains evolved to interpret sensory information using Earth's horizon and gravity as reference points. Without these cues, the brain creates new interpretative frameworks. During this adaptation, astronauts experience disorientation and perceptual errors as their brains attempt to process an environment fundamentally different from what they've evolved to understand. Psychological stresses further complicate perception. Extended periods in isolated, confined spaces alter sensory processing. The heightened vigilance required during space missions makes astronauts more likely to notice unusual phenomena, but also primes them to interpret ambiguous stimuli as significant. This could partially explain Vladimir Kovalyonok's heightened awareness during his sighting. Sleep disruption compounds these challenges. In low Earth orbit, astronauts experience 16 sunrises and sunsets daily, severely disrupting circadian rhythms. Sleep deprivation affects attention, memory consolidation, and perceptual accuracy. After prolonged sleep restriction, the brain becomes more susceptible to misinterpreting visual stimuli, a factor worth considering in evaluating astronaut testimony. Space agencies have developed training protocols to help astronauts navigate these perceptual challenges. This training includes recognizing common visual artifacts, such as lens flares, ice particles, and reflections from spacecraft components. Astronauts learn to cross-reference observations with instrument readings and seek confirmation from crewmates when encountering unusual phenomena. Documentation practices are equally important. Astronauts record unusual observations with precise details, time, duration, apparent size, movement patterns, and relationship to known objects. This structured reporting helps separate genuine anomalies from perceptual artifacts. However, these perceptual challenges cannot fully explain every unexplained observation from space. Multiple witness observations, where 2 or more astronauts independently report seeing the same phenomenon, significantly reduce the likelihood of individual perceptual error. Instrument confirmation provides objective verification beyond human perception. Duration also matters. Brief glimpses are more likely to be perceptual anomalies than extended observations. Applying these criteria reveals important distinctions in our cases. Cooper's radar-confirmed sighting provides instrument verification independent of visual perception. Kovalyanok's observation included corroboration from another cosmonaut and coincided with measured radiation anomalies. The STS-75 tether incident was captured on camera, creating a record analyzable independently of astronaut perception. These forms of confirmation suggest phenomena that exist beyond the perceptual challenges of space. The space environment creates unique perceptual conditions that can lead even the most qualified observers to misinterpret what they see. Yet these factors alone cannot explain all observations, particularly those with multiple witnesses, instrument confirmation, or video documentation. As we move toward evaluating the complete body of evidence, we must balance understanding human perceptual limitations with recognizing that some observations defy conventional explanation even after accounting for these factors. Evaluating the evidence, a scientific approach. When evaluating unexplained phenomena reported by astronauts, we need a systematic approach that distinguishes between genuinely anomalous events and those with conventional explanations. Scientific investigation requires clear criteria to assess reliability, particularly when dealing with observations from the challenging environment of space. Our evaluation framework rests on 4 key criteria. Multiple witnesses. When qualified observers independently report identical details, reliability increases dramatically, as seen in Kovalyanok and Savannika's corroborating accounts. Instrument confirmation, objective evidence like Gordon Cooper's radar tracking provides verification beyond human perception. Documentation, visual records, particularly the STS-75 footage, allow independent analysis and verification. Observer qualifications. Astronauts represent highly trained professionals whose careers depend on accurate reporting. Applying these criteria reveals significant differences in evidential strength among our cases. Gordon Cooper's 1963 observation during Mercury. Atlas 9 stands out because it combined visual observation with radar confirmation. This dual-mode detection is particularly valuable because radar operates on principles entirely different from human vision. When both systems detect the same phenomenon simultaneously, it substantially reduces the possibility of perceptual error or equipment malfunction. Cooper's report gains additional weight from his established reputation for precision and technical accuracy. As a test pilot and astronaut, Cooper underwent extensive training specifically designed to develop accurate observational skills. His consistent retelling of the experience over decades, despite potential professional risks, further strengthens the case. The combination of visual observation, instrument confirmation, and witness reliability makes Cooper's sighting difficult to dismiss. Vladimir Kovalyanok's 1981 observation aboard Salyut 6 features different strengths. The presence of a second witness, cosmonaut Viktor Savanik, who corroborated the sighting, elevates this case above single witness accounts. Multiple observers reduce the likelihood of individual misinterpretation. When 2 trained cosmonauts verify the same unusual phenomenon, the reliability increases substantially. What distinguishes Kovalyanok's case further is the reported radiation spike detected the same day. This measurement constitutes physical evidence independent of visual observation. Radiation detection provides quantifiable data measured with instruments, creating an objective record beyond testimony. The coincidence of visual phenomena with measurable physical effects suggests a connection between the observed object and environmental changes. The STS-75 tether incident from 1996 presents perhaps the strongest case due to its extensive video documentation. Unlike testimonial evidence relying on memory, the NASA footage creates an objective record that has been analyzed by independent researchers. This video evidence allows for frame-by-frame analysis, calculation of movement patterns, and comparative studies against known phenomena. Multiple technical analyses have identified aspects of the footage that resist conventional explanation. The object's movements often violate the predictable trajectories that debris would follow in vacuum. Their apparent passing behind the distant tether suggests substantial size rather than camera proximity. Their consistent disk shapes and luminosity patterns remain uniform despite camera adjustments, arguing against optical artifacts. The STS-75 case is particularly compelling because the video allows verification beyond the astronaut's perceptions. While astronaut testimony provides context, Footage becomes primary evidence that others can evaluate independently. This creates a level of documentation absent from cases relying solely on witness accounts. Buzz Aldrin's case, involving an L-shaped light during Apollo 11, demonstrates a different aspect of scientific thinking. Aldrin himself has consistently provided a conventional explanation. The object was likely a panel separated from their spacecraft's SIVB stage. This interpretation aligns with mission parameters and spaceflight physics. Aldrin's application of Occam's razor demonstrates scientific thinking rather than undermining his credibility. Ranking these cases by evidential strength places the STS-75 tether incident first due to its objective video documentation. Cooper's radar confirmed sighting ranks second, combining visual observation with instrument verification. Kovalyov's observation ranks third, strengthened by a second witness and reported radiation anomalies. Aldrin's case, while involving a qualified observer, has a conventional explanation provided by the witness himself. These cases collectively suggest that the strongest evidence involves multiple forms of detection beyond visual observation alone. When qualified observers report phenomena that instruments also detect or cameras record, the case for genuinely anomalous events becomes substantially stronger. This pattern indicates that some truly unexplained phenomena have been encountered during space missions, even if their nature remains unidentified. These historical incidents have influenced how space agencies approach unusual observations. The development of comprehensive documentation protocols, improved sensor systems, and specific training for anomaly recognition stem partly from these encounters. As we'll explore next, these legacy cases continue to shape how modern space programs balance scientific skepticism with openness to truly anomalous phenomena.